Ladies and gentlemen, boys and girls, welcome to another episode of Transparent Physics. In this lesson, we are going to be continuing our series on energy, work, and power. Specifically, we're going to be showing you some examples of the basic energy equations that were introduced in episode 1, the kinetic energy equation and gravitational potential energy. And real quick, at the end of this video, if you've learned a little about how to use kinetic energy and potential energy, please consider liking the video. If you have any questions about how I work through the solutions, always leave them in the comments below. And to stay informed of what's coming next from Transparent Physics and to help the channel grow, please consider clicking the subscribe button. On to the solution. Okay, so let's take a look at the problem. We've got a 1986 Nissan Pulsar, mass 830 kilograms, driving at 30 meters per second. We're interested in initial kinetic energy. We're interested in how fast you would need to go to double the original kinetic energy, and then how high would you need to lift it for its new gravitational potential energy to equal part A's kinetic energy. So let's real quick, let's take a look at some of the important ideas here. So when we're doing these calculations, I would say mass is going to be handy to know. Initial velocity, handy to know. What is the initial? So we're looking for, in terms of our unknowns, we want to know the initial kinetic energy. We're looking for how fast we would need to travel to double the original kinetic energy. And then we're interested in how high we would need to go to lift it for its new gravitational potential energy to equal part A's kinetic energy. So, some key ideas in there that we want to keep an eye out for while we're solving. And we'll just get going here then. So for part A, let's take a look here. There we are. Okay, part A. We are interested in the initial kinetic energy. Initial kinetic energy, what we're going to want is we're going to need to know the mass, 836 kilograms. We're going to need to know the velocity, or technically it's really the speed. We're interested in the magnitude of the motion. We're not interested in the direction. And I am going to do a sketch, but I'll do it for part C in this case. We won't really need it until that point. And what do we got? So we'll write the kinetic energy. Kinetic energy equals 1/2 mv squared. So we know the mass is 836 kilograms. We know the speed is 30 meters per second. Don't forget to square that. Very, very, very common mistake in introductory physics is you write it out and then you forget to square the speed. And it's only the speed that's squared. Also, sometimes what happens is I see students take 1/2 times 836 times 30 and then square all of that together. But the way that's phrased, it's simply the speed that is squared, not the entire term. All right. So if you figure that out, 388. We'll just, I guess, round it to here. Round a little bit. Again, the units for that are joules, kilograms, meter squared, second squared. And that's it for part A. Really just kind of a plug and chug. For part B, how fast would you need to go to double the original kinetic energy? Well, the instinct for a lot of people here is to say, well, if you're going to double the kinetic energy, you would need to double the initial speed. But let's see how the math works out for that. It may not be quite what you think. So what we're interested in is we're interested in, we'll say KE part B equals 2 times KE part A. And what would the new speed need to be in order to make that true? So what we can do is we can say KEB equals 1/2 MVB squared. And we're going to need to solve this in this case for V. Now when we solve it for V, we take the 1/2, we move it over, divide both sides by M. So we're going to see 2KE divided by M equals VB squared. And big pitfall here is kids would forget to then take that square root and move it over. So you need to make sure that your final answer is VB equals the square root of 2 times KEB. So there is a 2 in here anyway, but when we're solving for KEB is going to be the equivalent to 2 KEA. So I will, in full disclosure, the first time I worked this out, I actually forgot one of my 2 values, because I had a 2 in there for the equation manipulation, and I could have sort of assumed that that was the 2 for the value comparison. But we're plugging in 2 times KEA, because the new kinetic energy is equal to twice the original kinetic energy. So wherever we see the expression, let's go here. Wherever we see the expression KEB, we can replace it by the expression 2 times KEA. So that's what we're doing here. We're just taking the original expression KEB, swapping it out for 2 KEA, which is what our problem asked us to do. And then we divide that by the mass. So we take all that, we plug it in. So it's 2 times 388,400, and that is kilograms meters second squared, and so it's kilograms meter squared second squared. That is joule converted to its base units. And then we are dividing by the mass, which is 836 kilograms. And what we can see is we can see kilograms cancel with kilograms, leaves us with meter squared second squared under a square root. So the square root of meter squared second squared is meters per second. So when you run the calculations, you don't get double the speed in order to double the kinetic energy. You have to do less than that. It actually ends up being around 42.4 meters per second. So you don't need to go anywhere near double the initial speed in order to double your kinetic energy, because kinetic energy depends on the square of the speed, not the speed itself. And then part C. So what we're going to do is we're going to take our 86 Nissan Pulsar. I apologize for the quick and non-Nissan Pulsar sketch, but so what we're interested in is we're interested in how high we need to lift this so that the potential energy at part C is equal to the kinetic energy in part A. And we're just going to use that same value, then 388,400 joules. So in this case, we know that the potential energy equation is mgHc, and then we have 1/2 mVA squared. Okay, so we technically have a choice here. We already know the value for the kinetic energy. We solved for it in part A. So we could just plug that in right now. Also, though, another interesting opportunity presents itself, because we see that when we write the equation, mass appears in both terms. So we have a mass here and a mass here. So what we could do is we could just cancel those masses out and just go straight for the HC value. And I don't know, as my father would say, probably 6 in one hand, half dozen in the other. I'm not sure it really makes much of a difference. So let's just, we'll just go the algebraic route. So we'll just cancel out our masses, and we'll go straight for HC. So HC equals VA squared, and that's times 1/2. And then we need to take G and move it over. So if we take G and move it over, we're dividing both sides by G. So divide by G on this side, divide by G on this side. So we're going to end up having a G in the basement there too. I don't know. In hindsight, maybe not the easier approach, but so that's VA squared over 2G. Meters per second squared divided by 2 times 9.80 meters per second squared. Remember, don't put a negative sign in front of G unless you're in a kinematics equation. At least that's the way I play it. And let's take a look how this works out. So plug it into the old calculator, you get 30 squared. In the basement, watch out, and every time you have two terms in the basement, I like to put them in parentheses so that they don't separate from each other. You want to make sure that stays together so the calculation is done correctly. Alright, so when it's all said and done, I'm getting the answer to come out to be around 45.9 meters. So you'd have to lift up a Nissan Pulsar around 45.9 meters so that its potential energy, its gravitational potential energy, equals the kinetic energy that it would have driving at 30 meters per second. Okay, there we go. So we have a nice little overview here. We got a little bit of kinetic energy. In terms of just the base equation, we have manipulation of the kinetic energy equation, just to get practice with that. And then we have a comparison of kinetic energy to potential energy. Okay, then a couple closing thoughts real quick. Hey, I'm not saying that the things we just did aren't important. They are. You very easily could have a quiz asking you to solve for kinetic energy or potential energy. But in the big picture, knowing how to do those calculations in and of themselves isn't super handy. However, you take those equations and you tuck them into conservation of energy, which we're going to be talking about a little bit later in the series, and you can really do some amazing stuff with that. So this is an important lesson to get us used to these equations, because we're going to do some cool stuff as we go through this series. And as always, thanks for watching. Hopefully I've made how to calculate with kinetic and potential energy a little clearer on this lesson of transparent physics.